Today we're going to be graphing in the polar coordinate system, and we're going to talk about how to graph it, mainly by using our calculators, but we're also going to then be testing for symmetry. So certain graphs might have horizontal symmetry, vertical symmetry, or diagonal symmetry, and then we'll go through some of these types of symmetry that are listed in the table. So we're going to take a look at some polar graphs. And you have the link on your note sheet if you'd like to click it and look at these in more detail on your own, but we're just going to quickly glance through these. So a spiral is a common graph in the polar coordinate system, and this one is named after Archimedes. You can draw circles in the polar coordinate system. Roses, or sometimes called polar flowers, these have different numbers of petals depending on the equation. So as you can see, there's different types of roses that are created in the polar coordinate system. All right, and then we have a special graph called a limacon, and it's basically like a curve with a little loop-de-loop in the center. And there's special types of limacons called a cardioid, and you might figure out that cardioid means heart-shaped. This next polar graph is a lemniscate, and it's essentially an infinity symbol. So this is an example of how you create a straight line in a polar coordinate system. So it doesn't always have to be a curve. It could actually be a straight curve. All right, and then here's some additional graphs that someone has created. So if you're feeling adventurous, you can try different types of graphs in your calculator after we do this lesson and see what you can come up with. So now it's our turn to create the graphs. And so one thing you're going to need to do on your calculator is you're going to need to verify that you are in radian mode as opposed to degree mode. But then also we're going to go to this next line where it has function. So for function, that would be y equals. That's what we are typically graphing in on our calculator. But now we want to change this mode to be in polar. So now when you go to y equals, it has our R value, and instead of typing in x, when you hit the x key, it gives you theta. So this is actually our first equation, R equals theta. And so if you were to hit graph, and let's say you're in the standard window, just if you hit graph right now, you get a good graph, but we'd like to be a little bit more zoomed in and get a better picture. So this is a pretty decent picture that we're going to try to replicate on our polar graph paper. But I'm also going to do zoom fit. So I'm going to hit zoom 0. And we've done zoom trig before and zoom standard, but we're going to do zoom 0 to get this fitting a little bit closer up. And so now you can see that this is a spiral shape of our graph. So now what we're going to do is I'm going to go to my window, and I'm just going to verify that this goes from 0 to 2 pi. Let's say that yours is not going from 0 to 2 pi. Just go to your theta min and your theta max, and you could actually just type in 2 times pi, and that'll be substituted in there as a decimal. All right, and we're just going to leave this window for the rest of this worksheet. All right, so to fill out our table, we're going to go to table set because we want to have it start at 0, but then we're going to have it go up by pi over 4. I would say that typically pi over 4 is a good delta table. So that means that in your table of values, this theta coordinate is 0, and then pi over 4, and then this would be 2 pi over 4, which is pi over 2, and then 3 pi over 4, and then 4 pi over 4, which is pi. So we're going to copy that down, but I'm going to fill out the table with exact values for the theta values. All right, so as you can see, I've copied in my table of values. All of my theta values I have as exact, and all my R values I have as decimal approximations. So if these were x and y, and they were both equal to each other, that would form a straight line. Well, obviously in polar coordinates, that doesn't work that way, so this is going to end up as our spiral shape. All right, so let's recall how we label the graph of the polar coordinate plane. So we have 0, we have pi over 2, we have pi, 3 pi over 2, and 2 pi, which is the same as 0. And then halfway in between each of those, we have pi over 4, 3 pi over 4, 5 pi over 4, and then 7 pi over 4. All right, so the way that you're going to graph this is you're going to start with the angle first. So at 0 degrees, we're going to go 0 circles outward. And at pi over 4, we're going to go about 0.78 outward. At pi over 2, we're going to be 1.57, so halfway between the first and second circles. And then you're going to continue on. So now we have at 3 pi over 4, we have 2.35. At pi, we have 3.14. 5 pi over 4, we have 3.9. At 3 pi over 2, we have 4.7. At 7 pi over 4, we have 5.49. And then at 2 pi, we have 6.28. So there's only 6 circles, so we'll go a little bit past that. And as you can see, as the angle increases, so does the distance away from the pole. All right, so the last thing we're going to do is we're going to verify, is there any symmetry? Well, just looking at this graph, it doesn't appear to have any symmetry. Right? If I were to draw a line down the middle, whether it's horizontal, vertical, or diagonal, can I take the graph and fold it right on top of itself? Well, clearly not. All right, so then let's double check using these algebraic methods. So in number 1, it says if we substitute in negative theta in for theta, does it give you an equivalent equation? Well, if I do r equals negative theta, is that the same as the original equation, which is r equals theta? So let's use our calculator to verify. So if we want to try to verify, I have my original equation in R1, and then if I put in the negative theta in for R2, I'm going to hit zoom fit again, and we're going to see what we get. So my blue and red graphs obviously are not the same exact graph. It's not an equivalent equation. So this would not have x-axis symmetry. All right, so let's try to check for y-axis symmetry. So if we replace the r with negative r and the theta with negative theta, this divides, it appears to divide by -1 and get this exact equation. However, because we're limited to this domain, I'm going to suggest that we not use this check and instead do the third one. So if we substitute in pi minus theta in for theta, and let's see what we get. So the original equation was r equals theta. So instead of theta, we're going to put in pi minus theta. And then let's see if these two equations are the same. So if we go to the original equation, and then for the second equation, we're going to put in pi minus theta. We're going to hit zoom fit, and we're going to see if those are the same. So as you could see, the red graph does not entirely encompass the blue graph. And in fact, there was this little section over here that was added. And so this would not have y-axis symmetry. And you could also double check the fourth type of symmetry, and we could substitute in negative r instead of r, and that's equal to theta. And so is that, if we solve for r, we have r equals negative theta, is that equivalent to r equals theta? And we've already determined that from our first test that that is not going to yield an equivalent equation. And so therefore, as we suspected, there's no symmetry for this spiral. All right, so moving on to question number 2, we're going to graph our limacon, and it's r equals 2 plus 4 cosine theta. So again, we're going to do zoom 0, and we're going to see what our picture looks like. So if limacon is a fancy word for you, think of it as an eye of a peacock feather. It's got this oval shape with a loop in the middle. And so if we look at our table of values, we're going to fill in the decimal values for our radii here. So we have 6, we have 4.8, we have 2, negative 0.8, negative 2, negative 0.8, 2, 4.8, and 6. You can write down more decimal places, but since we're just graphing on this really tiny polar graph, then we don't need to be all that accurate. As a reminder of how to graph, we're going to go to 0 degrees theta, and we're going to go outward 6 circles, put in a dot. At pi over 4, we're going to go a little less than 5 circles outward. At pi over 2, we're going to be at 2. And at 3 pi over 4, we're going to be at negative 0.8. So as a reminder as to how to do that, instead of being on this side of the pole, we're going to cross over the pole and go 0.8 that way, but along that same line. All right, and then at pi, same thing. So we're going to go along this line, but instead of being on the same side, we're going to hop over it and we're going to go to 2 circles outward on the other side of the pole. 5 pi over 4, also we're at negative 0.8. So we're going to cross over the pole. At 3 pi over 2, we're at 2 circles away from the center. And then at 7 pi over 4, we're at 4.8, so a little bit less than 5. And then at 2 pi, we're back at 6. So as you graph it, kind of draw it the way that your calculator did, where you are drawing it in order. All right, so then after you draw it on your paper, then you make sure that it matches with what's on your graph. And as you can see, there are some points that are a little bit into quadrant 2 and 3, so just extend your graph to cover that, but still go through the points that you've plotted. All right, so in number 3, we're going to graph a limacon, but it's a special limacon that is heart-shaped. So if we change our equation to 3 plus 3 cosine of theta, now I'm going to hit zoom 0. And now instead of our loop-de-loop, it just goes to the pole and then bounces right back out. All right, so I've filled in my table of values now, and then we're going to graph. So at 0, we are 6 units away from the center. At pi over 4, we are 5.1. At pi over 2, we are 3 units away from the center. At 3 pi over 4, we are 0.87. At pi, we are at 0. At 5 pi over 4, we're at 0.87. At 3 pi over 2, we're 3. At 7 pi over 4, we're at 5.12. And then at 2 pi, we're back at 6. So as you draw it, again, make it look like what you see on your calculator. All right, and then always compare your graph with what you got in your calculator's graph and make sure that those generally match up. All right, so let's go back to questions 2 and 3. And it appears at first glance that we have x-axis symmetry in both of them. If you were to fold it along the x-axis, the graphs appear to fold right on top of itself. And so if we were to check algebraically, so the original equation was r equals 2 plus 4 cosine theta. And if I were to compare that to r equals 2 plus 4 cosine of negative theta, if you remember back to chapter 9, cosine of negative theta is actually equal to cosine of theta. So if you think about on the coordinate plane, if you go up positively, that angle, and if you go down negatively, that angle, they both have the same x coordinate for whatever point that is, whether it's on the unit circle or not. And so those x coordinates would be equal. And so no matter what we have here, cosine of theta or cosine of negative theta, it's going to be equivalent. You could do the exact same thing for number 3, but instead let's check with the graphing calculator. We could type in the first equation to be 3 plus 3 cosine of theta and the second equation to be 3 plus 3 cosine of negative theta. And then if you were to graph that, then you could see that the blue and red graphs are indeed the equivalent graph. All right, so for our final graph, we've got r equals 2 sine of 2 theta, which is a rose with 4 petals. And so if you go to look at the graph, you can see that it's got 4 petals. If you look at the table of values, I've got my table already filled in for you. And the one weird number in this table is at 6.28, which is 2 pi. You can see this as negative 4e to the negative 13th. So just as a reminder as to what that means, that's scientific notation. So that's negative 4 times 10 to the negative 13th. So if you take the number negative 4, which normally has a decimal after the 4, and you move it 13 spaces to the left, so now you've got point and then 12 zeros and then the 4. That's a very, very, very small number, which is essentially a 0. So I have only written it in the table as 0. And I think that occurs on your calculator because your calculator is approximating pi at some point, and so it causes this slight error in the r calculation. All All right, so we're going to graph this now. So we're going to have a point at 0, 0, at pi over 4, and then 2 circles outwards, and then pi over 2, and we're back at 0. And then at 3 pi over 4, that's where we're going to cross over the origin. So we're actually over here on the other side of the pole. And then at pi, we're back at 0. And then at 5 pi over 4, we're at 2. And at 3 pi over 2, we're back at 0. And then at 7 pi over 4, this is where we're crossing back over the pole, and so now we've got that point, and then at 2 pi we are back at 0. So now if you want to confirm with your picture, we need to draw that graph. And so we've got 1, 2, 3, 4 petals of our polar rose. All right, so this one appears to have 3 types of symmetry: x-axis, y-axis, and symmetry at the origin or the pole, which is like diagonal symmetry. All right, so we can check algebraically, we can check through the graphing calculator. So let's just do it with the graphing calculator. So the first one we would check is, what if we were to substitute in negative theta? So that'd be 2 times negative theta, or negative 2 theta. All right, so let's look at our graph now. And you can see that that red graph just covers up our original blue graph. So it definitely has x-axis symmetry. For y-axis symmetry, we would substitute in both negative r and negative theta. So if we divide by negative 1, we would get r equals negative 2 times sine times negative 2 theta. So let's draw in a third graph here. So we could have negative 2 sine negative 2 theta. And let's see if that graph covers up. So now we've got a third color. We've got our black colored graph, and that covers up our original graph. So that definitely has y-axis symmetry. And then if we were to check for symmetry at the origin, then that would be only substituting in the negative r. And so that would be the same as negative 2 sine of 2 theta. And so we'll put in a fourth graph here where we have negative 2 sine of positive 2 theta. And then let's see if the pink colored graph covers up our original, and now we did. So now we definitely have symmetry at the x-axis, y-axis, and at the origin. All right, so hopefully you have enjoyed creating some polar graphs, and maybe try some of these on your own and try to manipulate some of the numbers and see what kind of graphs you come up with. All right, have a great day.